So far, we've looked at ways to add a halogen to the ring, a nitrogen to the ring, and a sulfur to the ring. But we haven't seen any ways to add carbon to the ring, and in organic chemistry, being able to form carbon-carbon bonds is extremely important. This next reaction allows us to do just that. It's called the Friedel-Crafts Alkylation. And what the term alkylation means is we're putting an alkyl group on the ring. An alkyl group is just some alkane chain. Or it could be something simple like a CH3, or it could be a longer chain, or even something that's branched like an isopropyl group. You may have heard the R term before as an R group. When you see that R term, that's actually referring to an alkyl group. Sometimes it's used for other things, but really technically put, that R group should be just a simple alkyl group. If we have a halogen attached to R, like RCl, that's an alkyl chloride. And that's what we use with the Friedel-Crafts reaction. We use alkyl chlorides. So in this case, we have benzene, and tert-butyl chloride is the alkyl chloride. And what's going to happen here is this tert-butyl group is going to get added to the ring. So let me just circle what ends up being added. So this T-butyl, and specifically the carbon where the chlorine is at, is going to be the one that gets bonded to the ring in this example. So here we have our aromatic ring, and then here's our tert-butyl group. Here's that carbon that I highlighted in orange, and then here's that whole tert-butyl group that was added. Similar to the halogenation reactions that we learned about previously, this reaction uses a Lewis acid catalyst. In this case, it's aluminum trichloride. As for the byproduct of this reaction, what we're losing a hydrogen from the ring and the Cl from the alkyl chloride. So we can draw our byproduct as just HCl. Let's take a look at the mechanism for this reaction. It's going to be reminiscent of reacting Cl2 with the iron trichloride that we saw before. So what we're going to do is take our tert-butyl chloride, and the chlorine has lone pair electrons, so those are Lewis basic. And we're going to react this with the Lewis acid aluminum trichloride. So the aluminum wants those electrons, so we'll use a pair of electrons on the chlorine to form a bond. So now we formed that bond. The aluminum has a negative charge, the chlorine a positive charge. Now in this case, because we have this highly substituted carbon here, what happens is something kind of similar to what you saw with SN1 reactions where you lose a leaving group. Well, this Cl plus acts as a leaving group here, and we'll lose that. And what we end up with is a carbocation plus aluminum tetrachloride. Our carbocation is an excellent electrophile. Now we're going to talk about this later, but I'm going to leave an important note here for you. Because we have a carbocation intermediate, you always want to be on the watch for carbocation rearrangement at this stage. All right, so now that we have our active electrophile, which is the carbocation, we can react that with the aromatic ring. And let's do like we've been doing. And I'll go ahead and draw in a hydrogen, which is the one that we'll eventually get rid of. Let's react that with our tert-butyl cation. So I'm going to use a pi bond in the ring, draw a curved arrow to the positively charged carbon. Now we have our tert-butyl group added. We still have a hydrogen and a positive charge. All right, from here we want to reform the aromatic ring. And what we're going to do is use this aluminum tetrachloride. So that aluminum wants to go back to just the AlCl3, so we can do that by pushing out a Cl-, and that Cl- will come and take the proton, eliminate here to give us the aromatic ring. So we end up with our aromatic ring with the tert-butyl group. We get the HCl byproduct, and we get our Lewis acid catalyst regenerated.